Dear students, now we discuss some important properties of Laplace transform. First property is linearity. So Laplace transform is linear operator. That is, if alpha and beta are constants, and f and z are functions, then Laplace transform of alpha f of x plus beta g of x equal to alpha into Laplace transform of f of x plus beta into Laplace transform of g of x, or we may write alpha into capital F of p plus beta into capital G of p, where capital letters are Laplace transforms of functions given by small letters. Proof is not difficult. Uh, it is property of integration. Okay. So Laplace transform of alpha f of x plus beta g of x is nothing but, by definition, it is integral 0 to infinity e raised to minus px into the function under consideration, that is alpha f of x plus beta g of x dx. And now this operation is linear. That means we can write this as alpha. Alpha is constant, so we may write this as alpha into integral 0 to infinity e raised to minus px f of x dx plus beta integral 0 to infinity e raised to minus px g of x dx. And this is nothing but alpha into Laplace transform of f of x plus beta into Laplace transform of g of x, and this proves result. Second property is shifting property or translation property. The property is, if Laplace transform of function f of x equal to capital F of p, then Laplace transform of e raised to minus ax into f of x equal to capital F of p plus a. Note that here it is minus a, e raised to minus ax. If we multiply given function f by e raised to minus ax, then on right hand side we have to add a to p. That means L of e raised to minus ax f of x is capital F of p plus a. Here a is constant, where a is, which is a real number of course, a is constant. Let us prove. We have L of e raised to minus ax into f of x equal to, it is by definition integral 0 to infinity e raised to minus px into this function e raised to minus x f of x dx, which can be written as integral e raised to minus p plus a x f of x dx. Now, if we write p1 for this p plus a, then it is integral 0 to infinity e raised to minus p1 x f of x dx, which is capital F of p1. Okay, where transform variable is p1. Okay, so this is nothing but capital F of p plus a, and this proves the result. Let us see some examples and then we move to next property. First example is find Laplace transform of x raised to n multiplied by e raised to minus ax. A is constant. Now here we write f of x equal to x raised to n. Okay, so if we write f of x as x raised to n, then we know uh, its Laplace transform, that is capital F of p, is n factorial upon p raised to n plus 1. Okay, this we already have seen. And now the property is, shifting property is, if we multiply this function by e raised to minus ax, then the Laplace transform is f of p plus a. We need to replace p by p plus a. Therefore, by shifting property, Laplace transform of e raised to minus ax into f of x, that is x raised to n, equal to capital F of p plus a, and that is n factorial divided by, okay, we need to replace p by p plus a. So p plus a raised to n plus 1 Next example. Find Laplace transform of e raised to minus 3x into sine 4x. Okay, solution. So we define f of x to be sine 4x. Okay? Let f of x be sine 4x. Okay, we have capital F of p, that is Laplace transform of f of x is, okay, so this is of the form sine ax. So its Laplace transform is given by uh, a divided by p square plus x square. Okay, so this is 4 divided by p square plus 4 square, is 16. Now by shifting property, Laplace transform of e raised to minus 3x into f of x is capital F of p plus a. Here a is 3, so p plus 3, and this is nothing but 4 divided by p square is replaced by p plus 3 square plus 16. Okay, and you can simplify this denominator p plus 3 bracket square. Okay, so this is required answer. Now homework is find Laplace transform of e raised to minus 8x into cos of 2x. Okay, it is very similar to this. Example 3. Find Laplace transform of function f of x equal to 2x minus 3 x raised to 4 plus e raised to x into cos 7x. Solution. Laplace transform of f of x is Laplace transform of 2x minus 3x raised to 4 plus e raised to x into cos 7x. Now first we use linearity of Laplace transform. We have seen L of alpha f plus beta z is alpha into L of f of x plus beta into L of g of x. Okay, here constants are 2 minus 3. Okay, and we have three functions. Okay, so this is nothing but Laplace transform of 2x. It is nothing but 2 into Laplace transform of x minus 3 into Laplace transform of x raised to 4 plus Laplace transform of e raised to x into cos 7x. Here we used linearity property. In the next step, we use the property of another property of Laplace transform, that is, here first we use L of x raised to n. It is n factorial upon p raised to n plus 1. So this is 2. Here n is 1. So 1 factorial is 1 upon p raised to 1 plus 1, that is 2. Okay, minus 3. Here n is 4, x raised to 4. So it is 4 factorial divided by p raised to 4 plus 1, that is 5, plus now Laplace transform of e raised to x into cos 7x. So what is Laplace transform of cos 7x? Let us write down it as L of e raised to x into cos 7x. We write in the next step. Okay. So we call this as 1. Now L of cos 7x, that is L of cos of bx is p divided by p square plus b square. Okay, if this is b, then p divided by p square plus this square, 7 square. P divided by p square plus 49. Therefore, Laplace transform of e raised to x into cos 7x. Here we have e raised to minus ax. Shifting property, in the shifting property we have e raised to minus ax. So here minus a is minus 1. Okay, here a is minus 1. So this is equal to, we need to replace p by p minus 1. P minus 1 square plus 49. Okay, so here it is minus of minus x, that is minus of minus x. So a is minus 1. Now we substitute this in 1. Therefore 1 becomes Laplace transform of f of x equal to 2 upon p square minus 3 into 4 factorial. 4 factorial is 4 into 3 into 2. Okay. Is 24 divided by p raised to 5 plus this L of e raised to x cos 7x. So plus p minus 1 divided by p minus 1 square plus 49. Okay, so this can be further simplified. Now we move to next property. Here we discuss some examples based on linearity property and shifting property. Next property, it is called as change of scale property. It is described as if Laplace transform of f of x is f of p, then Laplace transform of f of a multiplied by x equal to 1 upon a into f of p by a, where a greater than 0 is constant. Okay, remember that Laplace transform of f of ax is 1 upon a capital F of p by a. Here a is positive. Later on we will discuss general thing, that is we allow a to be negative. Okay. Let us prove. We have Laplace transform of f of x equal to integral 0 to infinity e raised to minus px f of x dx. We call this as 1. Now we substitute z equal to x. Substituting z equal to x, we get x equal to z upon a. Second thing we get dx equal to 1 upon a into dz. Further, we can see the limits when x equal to 0, z is a into x, that is z is also 0. When x is infinity, z equal to a into x. It is also infinity because a is positive. Okay, so remember that if a is negative, then here z will be minus infinity. Okay, so here we are using a positive. Now we substitute all these things in 1. Okay, therefore by 1, Laplace transform of f of x equal to limits of integration are 0 to infinity, z equal to 0 to infinity, then e raised to minus px. So x is z by a minus p z upon a. F of x, that is f of z, dx is 1 upon a into dz. So this is equal to, a is constant, so we may write it as 1 upon a integral 0 to infinity e raised to minus p upon a into z f of z dz. Okay, now if we write p upon a as p1, then this is integral 0 to infinity a raised to minus p1 into z f of z dz. This is nothing but Laplace transform of f, function f, and the transform variable is p1. So this is capital F of p1. Okay, so this is nothing but 1 upon a into capital F of P by A. And this is a required thing. Okay, this is what we wish to prove. Okay, now what is the general thing? Note, in above property, we can have negative value of A. The general result is Laplace transform of f of x equal to 1 upon absolute value of A into capital F of P by A. Okay. Here, of course, we hold A equal to 0. Here, this mod A is absolute value of real number A. Okay. So remember that 1 upon absolute value of A into capital F of P divided by A. This is change of scale property. Now we move to next property, that is uh, Laplace transform of derivatives. Fourth, Laplace transform of derivatives. This will be very useful while solving differential equations. Properties: if Laplace transform of f of x is capital F of p, then first thing, L of f dash of x, that is derivative of x, derivative of f of x, equal to p into Laplace transform of f of x minus f of 0. That is nothing but p into capital F of p minus f of 0. We can generalize this to second order derivative, L of f double dash of x. Okay, of course we need to assume that second derivative exists. L of f double dash of x is p square into Laplace transform of f of x minus p into f of 0 minus f dash 0. Okay, or maybe p square into capital F of p minus p into f of 0 minus f dash 0. Okay, and the more general thing is third, Laplace transform of nth order derivative of f of x is equal to p raised to n into capital F of p minus p raised to n minus 1 into f of 0 minus p raised to n minus 2 f dash 0 minus and so on. The second last term will be minus p into n minus 2 order derivative of f at 0 minus f n minus 1 order derivative evaluated at 0. Okay, so note that if we are taking nth order derivative, then we should start with p raised to n into f of p. Okay, and then next term should be lower powers of p. Okay, so p raised to n, then we need to take p raised to n minus 1, p raised to n minus 2, and so on. Okay, and the terms are function evaluated at 0, its derivative evaluated at 0, and so on. Okay, so we have p raised to n minus 1 into f of 0 minus p raised to n minus 2 f dash 0, and so on. Okay, so the order of derivative, sum of the order of derivative and power of p should be n minus 1. Okay, so this n minus 2 plus 1 is n minus 1. Here also p power 1 n minus 2 order, so addition is n minus 1. Here p power 0 order of derivative is n minus 1. Okay, so anywhere the terms will of the form p k f n minus k or p raised to n minus k into kth derivative of f. Okay, addition should be n minus 1. So I need to write here k minus 1. Okay, here also. Okay, so addition is our addition should be n minus 1. Okay, so here addition is n minus 1, here also addition n minus 1. Okay, we prove first property, second and third are similar. Okay, so as usual we use integration by parts to prove first. So we have Laplace transform of f dash of x equal to, by definition, integral 0 to infinity e raised to minus px f dash of x dx. Here, while using integration by parts, we use e raised to minus px as first term and f dash of x as second term. Okay, because we are taking integral of second term. So this is first term e raised to minus px integral of second. So integral derivative f dash. So it is simply f of x. Limits are 0, infinity, minus integral derivative of first e raised to minus px into derivative of minus px it is minus p. Okay, so this becomes plus. Into integral of f dash, it is f dx. Now upper limit infinity. Okay, here it will be limit as x tends to infinity e raised to minus px f of x. Okay, so e raised to minus px will tend to 0, but we don't know about f. So we need to assume that this product is tending to 0. In most of the cases we get 0. Okay, in case f is unbounded, then uh, we cannot conclude anything. Okay, but here we assume that this product tends to 0 as x tends to infinity. So that first is 0. Second is e raised to 0 is 1 f of 0. Okay, so minus sign is there, minus f of 0 plus p, and this is nothing but Laplace transform of f of x. Okay, so this is p into capital F of p minus f of 0. Here we assume that limit as x tends to infinity e raised to minus px f of x becomes 0. Okay, second and third can be proved similarly. Now next thing is convolution theorem. Before that we discuss what is convolution. Okay, convolution. So we take two functions. Okay, and this is one type of product of two functions. It is called as convolution product. The convolution f star z of functions f and g is defined as f star z of x equal to integral from 0 to x, upper limit is x, note that upper limit is x, integral from 0 to x, f of x minus t, g of t dt. Here t is integration variable, w variable. Integral from 0 to x, f of x minus t, g of t dt. Note that this may be defined as f star g of x equal to 0 to x. We may write g of x minus t f of t dt. That is f star g of x is same as g star f of x. Now convolution theorem, important property of Laplace transform is convolution theorem. Fifth property is convolution theorem. Property is, if Laplace transform of f of x is capital F of p and Laplace transform of function g of x is capital G of p, then the Laplace transform of convolution f star g of x equal to Laplace transform of f of x multiplied by Laplace transform of g of x, that is capital F of P multiplied by capital G of P. Okay, so this is very useful result. That means the convolution product is transformed to usual product. Okay, so Laplace transform of f star g of x is f of p multiplied by g of p. Okay, so convolution product is converted to usual product. We are not going to discuss the proof. It is quite involved. Thank you.